All right. So in day 2, last day, what did we talk about? Okay, we talked about this thing called an expression. Expression doesn't have an equal sign, but expression is how do you get from one column to the other. So the relationship going left and right, like this. So if I ask you for an expression, in this case, we go, oh, to get B, you have to multiply A by 3. That's what I'm looking for when you say expression. I give you one letter, how do you get to the other one? All right? So this is the beginning of page 2 there, day 2, all right? Now, we said a relationship, a linear relationship, remember all the lines fall on a line, can be shown in a table, a picture, which is a graph, right? You can say in words. If you're saying it in words, you're saying for every increase in the x direction, how much does it increase in the y direction, right? So that's like your third sentence in describing the graph, right? Ordered pairs, that's the coordinates, x then y, and expression is what we just talked about, and graph. Okay, now finally, we ended off last day with these tables. So you're going to be asked to say, hey, is this data linear? That's easy to tell if you're given a graph. If you're given a graph, if everything falls in a perfect line, it's linear. It's harder to tell if you're given a table. If you're given a table, yes, you could graph it and see if the pictures make a straight line, then it's linear. But that's a lot of work. The easier way, yes, Alice?
Is if both the x and y go up by the same amount every time.
Yeah, so as long as it's consistently changing, so that like this one, it's going up by 2 each time, and over here, it's going up by 4 each time, we can say this is going to be linear. However, over this one, it went up by 1 each time, which is a good sign. But on this side, on the bottom, it went up by 3, then a 1, it changed. So it's not going to be linear. This is not consistently growing at the same rate. And when we drew the picture, it was easy to see. Okay, so we're going to do the same thing. So we're going to refresh that. Oops, where did it go? With these ones. So my question to you is, we have 2 tables here. We have a table on the left and a table on the right. Are they linear? So let's talk about the first table with the S and T. They're not? Why not, Sammy?
Because they don't go up by the same number every time.
What doesn't go up by the same number? Because I'm looking at S here.
S does, but T doesn't.
So S goes up by 1 each time, and but the T doesn't.
It's 4 and then
4. That's 6, and that's 4, and that's 6. So we can say not linear, right? The reason too, because T does not increase at a steady rate. I don't know. There's lots of ways of saying it. It grows evenly, it doesn't grow evenly. There's lots of ways to say it. As long as you're saying, hey, it's varying, or T varies, you can say that. Okay. Let's look at the H and the I. Is this linear? Okay. Sammy's saying yes. How's H changing each time? It's going down by 3. This to this is going down by 3, so minus 3 each time. How about I? How's this changing? It's going up by 3. Right? So we can say this one's yes, linear. Right? H and I grow consistently. Consistently. Okay. All right. So last question is example 3. Hey, come on. Okay. We're going to create a table. We're going to graph it. and a couple questions about it. Okay? So, first up, let's make the table. It says, how does it go? Mahisha has $100 altogether in $10 bills and $5 bills. Copy and fill in the table of values that show at least 5 possible combinations. So, what are the different combinations to get to $100 with only using only using $10 and $5 bills? Right. So we need to come up with 5 combinations. We can come up with more. Can anybody think of a combination? How can you get $100 by using only $5 bills and $10 bills?
10 tens.
10 tens? Sure. 10 tens, so that'd be 10 of these and 0 of those. That gives us 100. Lucas.
4 fives and then 8 tens.
So 4 fives gives us $20, and we need another $80, so 8 tens, that works. Any other combination you guys can think of that gives us? Yes, Alice.
25.
Sorry? 25s. So if we have 25s, that gives us $100. That means we need no $10 bills. Any other Max?
10 fives and 5 tens.
10 fives. Let's use purple. That gives us $50. And then you said 5 tens. That gives us another $50. Or 10 fives. So 50-50 makes 100. That works. Need one more combination. Yes.
9 tens and 2 fives.
9 tens gives us 90. Let's do green. And 2 fives gives us another $10. Okay, that's it. There's lots more combinations, right? So now the question's asking us, draw a graph of the data. And is it linear? If we look at this, our data definitely changes a lot.
Yeah.
All right? But the thing is, this is going up by 2, and this is going down by 8. Both of them are not consistent. This varies and this varies. We can only make that judgment call if something's linear or not linear if one of them is at least consistent. If one of them is saying is varying constantly, the other one's changing quite a bit, then you say it's definitely not linear. If both of them are changing, you can't make that judgment call just from the data. So we're going to graph it and have a look, right? So when we're graphing, rule number 1, use a pencil. Rule number 2, use a straight edge. If you don't have a ruler, come up and borrow. So all of our data is positive, so we only need to use the top right-hand corner of the quadrant. So we're going to draw our axes on the outside edges. So we're going to go here, draw our axes, like so. One this way, one this way. All right. Now, before we can start throwing data down, we need to label our axes. What's on the X, what's on the Y? Sam. Sorry, not Sam, sorry, Max. Max.
Number $10 bills and number $5.
Which one's on which?
Tens on the bottom.
10's on the bottom. So remember the order that the table is X, then Y. All right? That tells us how the information goes on the graph. So X is left and right. So that's number of $10 bills. So I'll shorten that, number of $10 bills. And on the other side, number of $5 bills. All right. So our graph here has 10 lines going in both directions. Right? Looking at the $10 bills, I think there's 10 lines, maybe 11 lines.
Yeah.
All right. our beta our biggest number is 10. Right? So it makes sense to make everything just worth 1 for the 10. Right? But remember, we don't have to label every single line. We can label every second line to make it a little bit nicer to read. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we have 0 here. Okay? Okay, let you guys write that down. But going in the other direction, our biggest value is 20. So how do we gotta do our spacings here? What do you think, Max? Each line is worth 2, right? That'll make sure all the information fits in, right? If you go by ones, everything's not going to fit in. So we can go, you can label every single one, or you can label every second one if you want. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. All right. So now we want to graph our information. Okay. Our first point is 10 for the x and 0 for the y. So I'll do that in red here. So at 10 and 0. So I'm going to put a, are you guys done drawing the axes? Or did I go too fast? No? Give you guys another couple seconds here. Okay. So 10 and 0 is here. Okay. Then we have 8 and 4. So we just start at 8, we go up to the 4, we put a dot, 8 and 4. We'll do that in orange. Oh, I should color code this. That was blue, that was orange. Then we have a green, 0 and 20. Right? So then we're doing this one, x at 0, y at 20, puts us a dot way up here. Okay? Then we have 5 and 10. So x is at 5, up to 10, so a dot right there. 5 up to 10, dot right there. And finally, yes, Alice?
It's linear.
It is linear. We go 2 and 9. Right? I'm sorry, 9 and 2. 9 here, up to 2 there. So look at this. Is this linear? Yeah. So we can draw a line through all of our points, and it's going to make a straight line. And so yes, this is linear because all the points fall on a straight line. Okay, so this line that we've drawn here represents this relationship. That's the whole point of this line. It's like, what are all the different combinations that you can make $100 using 5s and 10s? We could have, we didn't pick this point, we could have picked this point here. Let's highlight this in pink. Oops, no, that's not a highlighter. Well, that's a horrible thing. Oops. Like this point here. We could have done this one here. We didn't pick it. We could have picked 7 $10 bills, which is $70, and 6 $5 bills, which is 30. Right? 70 and 30 makes 100. Or we could take this point here, or this point here. We could pick 4 $10 bills, which is right here, which is $40, and 5 $12 bills, which is 60. Right? So this line shows us all the different combinations for this relationship to work. This picture is this relationship. All right? Yes? Can you wait a moment? Ashton's going to go first, right? We're still waiting for somebody to return as well. Okay, so now the last question. Is it possible for this person to have 19 $5 bills? Alice?
No, because then when you added the rest would be 10, and then when you added those, it wouldn't be able to add up to 100.
Yeah.
Because it's an odd number.
Yeah, so if you go 19 times 5, you get $95. There's no way to make up the rest of the money using $10 bills. And if you use our graph, so you can explain that using the logic that Alice did as well right there, which is beautifully said, or you can use the graph as well. You can say that, hey, at 19 $5 bills, this is my graph. Right? It hits here, so the rest of the money is going to come from over here. So if I go down, this says I need less than one. One $10 bill, which is not a real thing. Right? $10 bills come in a whole amount. 1, 2, 3, 4. Right? So that's why. So now this line is a mathematical line. Yes, you can multiply a decimal number mathematically to make it work, but in the real life context of the problem, this doesn't make sense because you can't have less. You have to have a whole bill, right? So you need to put the practical situation in here as well, right? That's it. Okay. All right, so we're going to work